Hello, everybody. Hey there, good afternoon. Thank you for coming today. I know the screens outside, it might have got a little confusing. It's talking about all kinds of other people's talks, but if you're here to talk about extreme scale and Azure Functions, you're in the right place. Trust the website, I guess we could say. So anyway, my name is Paul Yuknewicz. I'm the head product person for Azure Functions and Serverless. My team designs and operates some services at Microsoft, Azure Functions being the main one. And we support the overall serverless efforts like container apps, Legion, and some of the other services that are underneath. What I want to do today, I want to do something a little bit different. And thank you for coming to hear about with me. I want to double click and really go under the hood of Azure Functions and talk about how we built it and talk about how we made it scale. And when I talk about scale, I'm talking about things like bursting of instances, let's say 1,000 plus instances in under a minute, or being able to handle over 1 million messages or requests per second. That's the kind of scale I'm talking about. So today, we're going to go through a number of things and hopefully give you a good idea of how it works. You'll hear some of my opinions. Why did we do it this way? Why are we thinking about this way? And after this session, I'd love to get your opinions too. And I also hope to share some tips and tricks that we've learned the hard way along the road, and maybe you can apply that to your own apps in your own services as well. Does that sound like a good plan? All right. So this is about the only overview slide I had. Azure Functions was designed from the ground up to be all about event-driven apps, event-driven architectures, event-driven scale. You can see a number of scenarios I have up on the slide. I think serverless and functions probably started as being a handler for when blobs are uploaded, run a little bit of code. If I think way back to when I first saw AWS Lambda, and I wasn't working on serverless at the time, I admired how now you can not only upload data into your buckets, but you could also run a bit of code and do some processing. I think that's where it started. What it's evolved into is what you see here. So you're doing real-time data processing. You're having event streams coming in, fire hosing you with information, and you have the chance to ingest that data, analyze it, transform it, do all the things you need to do. And a lot of times, something like a function is maybe a companion to the rest of your application. So I've seen it before. I don't see too many applications that are, let's say, 100% functions, but I see an awful lot of applications that have functions that help get data in, transform, and send data out. It's also really handy for simple APIs, like if you want to have some back-end processing, even some heavy lifting, some computation. Doing that with functions can be simpler than making full-blown API apps. And now, you've probably heard a little bit about AI from us at Microsoft and from the whole community. Maybe you're working on it too. But we're seeing functions are really interesting to handle the different workflows and orchestrations you do in AI pipelines. So like I said, functions has always had a superpower for taking data in. And when you work on an AI app, let's say with RAG, the very first step you do is you take a bunch of data in and you embed it. And so functions become really handy for that use case. And also, if you look on the top right, we have the ability to do actual proper workflows and orchestrations. If you kind of take a step back, most any enterprise process where first you do this, then you do that, maybe you do a few things after that, and you need it to be durable and reliable, those end up looking like a workflow. And for those of you who've tried to build one of those yourself, you can do it, but it's a bit tricky to keep it reliable, right? You have to do queuing and outbox patterns and journaling and event sourcing and all kinds of patterns to make that happen. And the cool thing is with something like durable functions or also Dapper workflow, we actually have the technology where you write the kind of code you want to write, and you get that kind of orchestration and journaling built in. And you even get sagas and compensation logic just by doing try-catch style code and doing your compensation logic in the catch. So anyway, here's a bunch of scenarios that I think about for functions. And the bottom line is we've learned over the last several years from you, we had to scale a lot better. And I'm really excited. We've been working on Azure Functions Flex Consumption Plan. Folks heard about Flex Consumption? in the room? Well, I'm going to talk a lot about it, but that's a completely rebooted plan, completely rebooted architecture where we rewrote functions to hit the next 10 levels of scale above what we've been doing. So now you can get to that like bursts of thousands of instances in under a minute. So that's the overview. A few things. This is the structure of how I'm going to approach things today. I'm going to do kind of things a little bit in the opposite order. I'm going to show you some resources so that if you want to try the CLI commands, look at the code yourself while you're sitting here, that's cool. And you'll have it. And then I'm going to do a demo. And then I'm going to do a bunch of kind of going back and forth between architecture. Here's some architectural decisions we made. And then when I can, I'll try to illustrate it with a demo or something tangible. And then we'll do some tips and tricks. OK, so getting right into it. Hopefully, this is the only thing you'd have to screenshot, because I'll share things afterwards. If you go here, everything about what I'm going to show you, notes, CLI commands, it's all up there. And if I forget something, you tell me, and I pop it into the gist, and it just goes there. So hopefully that helps. All right, so let's talk about testing at scale. And the way I think about this is we need to be able to scale in all the way to 0, where you're in a serverless billing model. You're not paying anything if there's no executions. But we need to scale out. I exaggerate. I say to infinity. But you want that near infinity feeling where as much as you want to scale, as much as you're willing to pay, you're going to get that horsepower from the cloud. And then it needs to be elastic. So you need to be able to scale huge, scale back in, scale out, scale in, over and over and over again. And that gives you the good economics of using serverless. OK, so a little bit of setup for this. The way I've thought about scale, first, it's always I have this motto with the team, measure, measure, measure. And so the things I want to measure for scale, the number one thing I always measure is throughput. So it's like how many requests or how many messages per second can my app handle? And I think about that from the external clients. The clients are pumping messages in. The clients are pumping in HTTP calls. And how much could I process per unit time? That's the most critical. And I want to, at a very bare minimum, I want to be able to handle tens of thousands of requests per second. But with a lot of scale out, I'd actually like to be able to handle millions. And so that's the benchmark that we thought about. For latencies, cold start has been one of the things Azure Functions has had some challenges with, honestly. And we've worked a lot on that. So we want to measure those latencies also. And being a little bit scientific about it, we want to look at a median or a 50th percentile latency. We also want to look at the 99th percentile and just see how we're doing for our end users. We want to keep those error rates down. Obviously, that hurts resiliency, and it also affects your performance. I'm going to keep an eye on the CPU and memory. The reason why I do that is while I'm running at this throughput, I want to see if any part of my hardware stack is going hot. I want to see if my CPU is maxing out. I want to see if my memory is maxing out, because any one of these ceilings could be the reason why your app won't scale. And I'm going to go into it a lot, but kind of a rule of thumb is how do you get to about 70% utilization of your hardware? 70% CPU, 70% memory in a steady state, so that you've got a little bit of room left. Your users are getting a good experience, but you're also getting the value out of what you're paying for, right? So you want that high throughput with high utilization, and you're going to balance the two. Another thing that's super important, and whenever we partner with customers who are working through scale, it's important to look at the queue depth. So if your app is based on queues, if it's based on messages, I like to look at how many messages are piling up in the queue, going unprocessed. And that's also a very good observable metric to know if you're scaling properly, right? Because if you're not processing your work, that means your users are getting a bad experience, or maybe you've even just configured the functions in a non-desirable way. So even though you're giving lots of instances, lots of power, still you're not actually processing and getting the results. So it's kind of like almost an output metric is how low can you keep that queue depth while you're keeping the throughput extremely high. Make sense so far? So far, so good? Does this kind of resonate? Maybe those are things you look at? OK. All right, so now getting more tangible. Here are the exact goals that my team set. With the new plan, which by the way is public, it's in public beta right now. So the flex consumption plan, we set out to do 1,000 RPS as just table stakes, a absolute baseline, 1,000 requests per second. But we want to be able to do millions of requests per second through scale out, through heavy load. So that's the goal. And we literally, we actually run over 80,000 tests a day on all aspects and all SKUs, testing the heck out of functions and also watching its trends so that we know every day how close are we getting to these goals for you. So that we make a huge investment. It's a really big deal. The next thing is we want to look at bursting. If you look at Elastic Premium, which is kind of the most expensive plan, the best plan we've offered to date, it can take, I mean, if you want 100 instances, it can take many minutes. It can take a half hour. And we don't want that anymore. So we wanted to be able to scale to 1,000 instances in under a minute. That's the benchmark that we want to do. And we want to do even hundreds of instances in a few seconds. And then, think about the message types. We have both HTTP and non-HTTP message types, and they have very different kinds of scale requirements. Like think about HTTP comes in through a load balancer, messages are in the background, so we need to be able to handle both kinds of cases. And we don't want to just do hello world, we want to do a real beefy kind of application. And we need to be able to do it on a private network. So this new plan, Flex Consumption, actually works on VNet with private endpoints. So it's got the complete access to the private network. You can do things securely if you're in an enterprise. And I'm going to talk about concurrency in a bit, but concurrency is one of the other magic dials we have to further optimize, are you getting the most right-sizing your instances? Okay, so that's the goals. Now let's talk about an actual test that we're going to do right now. So what I'm going to do, I've got an end-to-end, it's simple, but it's a real end-to-end application that's going to process telemetry. So I have a big application, let's say a big distributed web application. It's creating all kinds of telemetry as users interact with it. And it's going to send the telemetry as HTTP posts with JSON, having a payload of, here's the user, anonymized, here is any click metrics they have, here's any feedback they have, here's their experience, and we send it through the system. Now what the HTTP function is going to do, it's going to transform and convert those into Event Hub stream messages. And then I have a number of downstream analytics and persistence mechanisms that'll basically let me store and work with the telemetry after it's done. So it's kind of like data ingestion with analytics. That's what this function's doing. And for a load test, I'm going to use the new Azure load test, which is a kind of a reboot of what we used to have with Azure DevOps, but now there's a new Azure native one. And that one we're going to set up to do 1,000 plus RPS with 4 agents, 250 users each. We're going to do HTTP posts. I'm using Flex Consumption. Flex Consumption is inherently Linux. I'm going to use the default SKU, which is 2 gigabytes. I just happen to use .NET 8. We support all the languages that Function supports, so don't stress that I did .NET 8, but I wanted to show you that one. And as I show, mechanically, this is an HTTP trigger in, and it's Event Hub bindings out. So it's an example of using multiple of the triggers and bindings together, which is oftentimes what we see in functions. All right? And like I said, I'm going to use the metrics that I'm looking for. I want to look at that throughput. I want to look at the CPU. I'm going to look at the scale logs and all kinds of stuff at the same time. All right, so that's the approach. Enough PowerPoint. Let's go to a demo. So I've got this application. Let's make it a little bigger. So I have this end-to-end application that I described. It's up on GitHub now. So we call this one HTTP VNet Event Hub. So again, it's HTTPN, Event Hub's out, everything on a VNet. And the core function code here, if I go down to the source, I have this process customer feedback, and it's incredibly simple. But again, I'm seeing that I've got an HTTP trigger in. I'm going to process the data. I could do any more transforms I want. And then I'm going to use the tuple syntax in C# so that I'm both going to send a proper HTTP response code, like a 200, and I'm also going to send an event. So you can actually have multiple output bindings in functions. I'm going to send multiple outputs. And on the output, as you can see here, I'm simply sending to an Event Hub topic subscription. And so any subscribers, like databases, other analytic streams, can now listen to this telemetry stream spigot as it comes through. So it's a pretty simple function. And the payload, here's what it looks like. So for my load test, I'm going to have feedback that kind of looks like this. So we have both telemetry and feedback. Users can submit feedback. Telemetry is collected by the system. And this is a sampling of what that feedback will look like before we process it. All right, now I'm going to go over the portal. And I've got all kinds of resource groups today to try to pull things out of the oven for you. Let's focus on this one first. This is the deployed app. And all the things you can kind of expect are here. I've got my function itself. I've got my Event Hub's namespace. My Event Hub is in there. I've got all the monitoring, and I've got even private networking. So we're seeing where this is all behind a VNet. And I've got a load test. Let's go up to the load test. Bear with me at this resolution. It's a little tricky. OK, in this one, it looks like I don't have it, but that's no problem. So we made it easy in functions. If I click on this Better Together tab, forgive us for the name. We're working on it. But if you want to attach this I joke because the team was supposed to be like, yeah, like let's put some services together that are better together. That's the strategy. But then all of a sudden it showed up in the UI. Anyway, life's a journey. So let's create a load test, which is better together, and we are going to create the test. This is actually pretty cool. Like it already has the context of my function that I want to load test. So when I go to add a request, all I have to do is like give this thing a name. So let's call it process feedback. And I pick the actual function that's deployed, process customer feedback. And you can see it's already figured out the route. And it knows that it's a post. And then I can go to the body, and I can push the payload that I want to. Let's just use this sample that I already had. All right, so I have an array of JSON objects that'll get pushed in. And that's my load test. I mentioned I wanted to get over 1,000 RPS. I know just by kind of reading the docs that if I have 4 instances with 250 users per, I'm going to get at least 1,000. I'll probably actually get more. And so that'll be a pretty sweet load test. And also, you can do these different, do you want linear? Do you want steps? Let's just do linear. So that's just going to mean over a function of seconds, over 5 minutes, it's going to do a ramp up. And actually, that's 20 minutes, which my boss might not love the cost that comes from that. So let's dial it to 5. He won't mind. All right, let's go and we'll do a create. So that's going to create the load test. And I'll probably have to find some other things to talk about while I do that, because this takes about 2 minutes. So let's look at our clock. 3:19. All right, while we're doing that, let's get set up on the other side. So let's look at how do we monitor this thing. I've got way too many resource groups. So this is the resource group we were looking at, right? This Flex Event Hubs Oslo. Flex Event Hubs Oslo. And let's go to App Insights. App Insights, just so you know, this is the monitoring product that I would say is really built in and just super well integrated with functions. If you ever want to look at telemetry, you either want to look at logs, distributed traces, they're all in here. And this is kind of a cool thing. You probably know this, but not only can I do things like see actual transactions that have happened in the last few minutes or the last few hours, I get visuals over the topology. I guess I need to send some traffic to it. And I get some live metrics. So as soon as I start producing traffic, I'm going to see them here. And that's part of my setup. So I don't see any yet, but that's expected. It's still provisioning my load test. The load test, actually, I could talk about this for a second. So I actually worked on starting the load test service too, and it's built on top of a Kubernetes cluster, and the Kubernetes cluster is actually serving up JMeter. You folks use or know JMeter? So we wanted this load test to be a lot more flexible, and it just looked like the community had bet pretty big on JMeter throughout the years. There's other really good ones too, like there's K6 and other up-and-comers, but we went with what most of the community understood, and that's JMeter. So when I run this load test, and I even set it up, remember it said, here's your function, here's the post, here's the payload. What that actually did is it outputted a JMX file. It created a JMeter script, and that's fully customizable. So if you have your own JMeter that's done more of a capture of live traffic, or if you know how to customize JMeter, you can plug it in here too. In this engine, what it's responsible for is like creating a fan out, a huge scale of that load with a bunch of regional instances pounding that endpoint. And then it does the monitoring, of course. So that's a little bit about the load test. Let's see how we're doing here. We're not quite there. All right, so well, I'll fill a little bit more time. I mentioned some of those metrics. So the request per second, the big one I'm going to be looking at here is the request rate. And we're also going to keep an eye on the servers. Now, this is a really fun one. Oh, here we go. Watch this. It looks like it's going. So we're ramping up right now. So pay attention here, and also watch the servers. As it needs more servers, it's going to really quickly burst them. Look at that. It just went from 3 to 30 in just a few seconds. And now we're reaching a steady state of 2,000 requests per second. So this is pretty awesome. Like, this is... we totally couldn't do this before. Like consumption functions couldn't give you this many servers, and it couldn't give you this fast. And again, even Elastic Premium really struggled. Like you'd be getting, maybe 10 instances per minute, but now we can do 1,000. So you're kind of seeing this live. Some other things I'm going to be looking at. If I scroll down here, I want to make sure that not only am I ingesting those messages, but also I'm making a good use of my hardware, and things are healthy. So I see that my exception rate is 0, which is good. So I'm not getting user exceptions, I'm not getting functional exceptions, and I'm not getting scaling exceptions. Like I'm not seeing rate limiting. You want to watch that one and make sure you're not getting rate limited. All right, and then here I'm looking at my memory and my CPU percentage, and notice how it started with a lower number of servers, and the utilization was about 50%. Then as it added close to 89 servers, the CPU went down, let's call that, what do you think, 25? It's in the 25% median. I'd say that's okay. So like we accomplished one goal. Like we scaled incredibly well, no problem. But the thing I'm going to ding us on right now is we're not being very efficient. We're only using 25% of the hardware we're already paying for. And I want to be as efficient as possible. I want you guys to save money. And only pay for what you need. And that's going to be the magic of this thing. So the way we're going to address this is through concurrency, and that's the very next topic. But I just kind of want to place a mental note. Like, we accomplished one goal, but we didn't accomplish every goal. But pretty cool. That's flex consumption. You like that? OK, so definitely, for I would say, in general, when you want to do event-driven on Azure, start with flex consumption functions. Like I said, it's in beta now. It's going to go GA before the end of this calendar year. And it's just built from the ground up for this scenario. All right, so let's go back to slides. And all right, so what we just did, that's not the right slides. I'm sorry. I've got even better, more special slides for you. There we go. All right, so we did the load test. What I'm going to show you here, this is a real example of a customer that we've been working with since the beginning of this calendar year. So like early, about January, February in 2024, we've been working with a little website you might have heard of called GitHub. And GitHub they did this exact scenario that I just showed you. They're doing telemetry ingestion for all the GitHub sub-apps that live on it, right? So let's say you're working with GitHub Actions. Let's say you're working with the source code control. You can think of all the different apps and stuff they have. That creates a whole bunch of telemetry. And what they found is that their message and queue ages got way too high. They just couldn't keep up with it. But they were hopeful to do this using something like Functions that's serverless. And they didn't want to stand up Kubernetes clusters that they really had to do a lot of operations just for telemetry, right? Because what they want to do is they want to run GitHub. GitHub is their main business. They don't want to run telemetry. Telemetry is just a necessary evil to operate a service, right? So they kind of took a bet early as we were new software. As you can see here, they were able to achieve 1.6 million requests per second as a steady state. They're actually doing even a little bit higher now, so it's cool. They're a great design partner, because as we find issues, we're finding them early with GitHub, and we're able to get more scale and more efficiency. Another thing about this graph that's pretty fun is when you see that the scale kicks in, look at the y-axis is basically showing you the message depth, how many messages you have. It's just boom. It's like plowing through that queue and keeping them at a low queue age, queue depth as a steady state. So that's, as you even measure your own performance, this is the kind of graph that you'll want to see. You want to see that you can quickly take care of any backlog and then go steady as messages are coming in, you're knocking them down. All right, so let's talk about the architecture. My team might get a little mad at me for this. I'm going to show a bunch of internal stuff to you, but I think it's important. Maybe it'll increase your confidence in the service, because I want you to know how this works. And you can kind of understand some of the things we went through, and maybe that'll help you as you build these apps as well. Okay, so let's go through the architecture. It's a bit of what we call an eye chart. There's a lot of stuff going on. But on the left-hand side, what we're seeing is our Antares infrastructure. Antares is our code name for anything that has to do with app services or anything that has to do with functions over the years. This is the compute infrastructure that runs app service and that runs functions. Literally gives you the instances, literally gives you the VMs and stuff like that. And also, each colored box represents a role or a microservice inside of the stamps that actually make this thing run. So it's interesting. We talk about microservices. Functions is an alternative to microservices that makes your life a little bit easy, but it's actually built on top of microservices. So we actually use that pattern ourselves, and that's how we achieve some of the horizontal scale internally as different parts of the system go hot. All right, so focusing on the left side, this is effectively the set of controllers, the set of bossy microservices that manage the rest of the fleet. And as I get to the right-hand side is where your workers, worker in my vocabulary, all that means is your application, your zip file that only you could write. Those run as workers. Everything else is the host. So the function service is the host. Your code runs in workers. So on the left side, we'll focus on the host. We have this microservice that we call the front end. In the front end, as you would expect, that's the front door for your end users. When they make HTTP requests, everything comes through that front door, right? When you saw that, even the web browser, let me come out of here for just a second, just to kind of visualize it a little bit. If I peek at my function itself, let's go down here. An HTTP function comes through a URL, right? And this domain, this AzureWebsites.net, everything goes through AzureWebsites.net. That's our front door. So it's all going through our load balancer. And the good thing about that, kind of like any proxy, since everything goes through that proxy, we have a lot more data about what your end users are doing. We can monitor it. We can understand how much scale needs to go through it. And we can do a lot of placement, right? As traffic comes in, we can route it. We can place it based on the load and based on a number of things. So I'll come back here. I'm going to keep doing this. Hopefully it doesn't irritate you, but I'm going to try to show you visuals as I talk through the architecture. And sorry, my hotkey didn't work. OK, so that's the front end. So the front end, it load balances the traffic, and it monitors the traffic. That's very important. And then it's got a subcomponent within it called a scale controller. And the scale controller basically is looking at the traffic and also looking at your function app itself, like, oh, it's an HTTP app or it's an Event Hub app, and here's the concurrency that it's expecting. So based on that, I'm going to make a decision. And it actually votes. The scale controller votes. Should you have more instances? Should you have less? And it's the thing kind of orchestrating the whole rest of the system. So it's making votes. Then we have the data role. That's the next green box on the left. The data role is responsible for placement. It places and schedules your work. And it's going to do a few things, like it's going to talk to the stamps on the right-hand side to see how much capacity you have, and it's going to make a decision if you need more, less, or need to stay the same. So it's in constant communication with the fleet, deciding how much compute is available to you. And that's how we keep you efficient. That's how we keep you elastically scaling. Now, being in the business that I'm in is a little bit rough, because to make that kind of experience happen for you, I'm managing a huge pool and fleet of VM servers on the right-hand side, a gigantic one. That's how we pull this all off. And that's why I wouldn't recommend that everyone here goes and builds a serverless PaaS, because it's tricky. These are the kinds of things you have to deal with. But it's worth it for us. We got there. The next microservice is the controller and the functions pod service, or FPS. You could kind of think of that as the data role is being bossy. It's saying, hey, give me some more servers. Take some servers away and drain them. It's being bossy, requesting what it wants. The controller is actually doing the work on the right-hand side to do those lifecycle events. It will create functions. It will start functions. It will stop them. It will drain them. It will destroy them. It can do all the actual actions. So it's actually kind of the technical implementation of how we pool your applications, where the data role is more saying, here's the desired state. So data role is saying, here's the state I want. The FPS is actually implementing it. And then at the bottom, we have some databases. Historically, when we started out, we did all state management using SQL Server. And SQL Server is a great backend. And when I say state management, there's things like the life cycle, like what state should your VMs and your functions be in? Is there any transaction that started? Well, we need to journal it to keep it reliable. So all that state management has been done in SQL. But we decided to kind of pull off this kind of scale. We added Cosmos DB because it actually has the best latency characteristics of all the databases in our fleet. It almost behaves like a cache. So when you're doing state management, working with something like a cache is really desirable. We could have used Redis as well. We evaluated it. But Cosmos gave us the experience we wanted, and it did it regionally, which is what we also wanted. So that's that side. And then on the right-hand side, I'm going to do another double click on this, but we have something called Legion. And Legion is our custom compute that we built for you guys just for event-driven and container scenarios. So if you kind of think of ordinary compute, you can create a VM or even a VM scale set, which gives you large units of virtual machines that are pretty static. They take a few minutes to create, and they're good for a set of workloads. But in our case, we want an event-driven function, an event to come in, boom, create the container, create the app, process the request, and then go away. So it's much more ephemeral. It's much faster. And so the way that we do that is we take a whole bunch of VM scale sets, and we subdivide them, and we chunk them into nested VMs. So we use Hyper-V nesting, where you have Hyper-V running inside of Hyper-V, and we chunk up this fleet of VMs. And that micro VM now becomes your pod. That's the place where your code can run. And we actually literally do use containers as well, just for our own DevOps efficiency and for our own speed. So we'll literally carve up micro VMs that can run pods of containers. And that, in the end, is where your function is going to run. And we're doing that kind of orchestration on your behalf of creating pods. And there's some complexities here, too. And I'm going to get into it more. But like, if you're running different runtimes, if you're running .NET 6, .NET 8, Python, Node 22, Java, all these things, like they all need different container images and they need different specializations. So we actually need to maintain pools of every permutation you can think of. And I'll get into this, we call these placeholders. But one of the big tricks we do to get past cold start headaches is we create these placeholder pools that are like extremely close, probably to what you're going to run. The only thing that's missing is your actual application, so we can specialize it and serve it to you. So a lot of the game with functions and serverless, it's not about making the VM start quickly. It's about having the VM already started and then specializing it super quickly with your app. That's actually the game that we're in. And as you can see too, there's a lot more going on than just optimizing a VM, because we have to optimize the load balancer. We have to optimize the concurrency. We have to optimize the number of instances you have. We have to do state management. So there's so much more to it, and that's really kind of the business that we're in. So a little bit more vocabulary. I'll spend just a little bit of time on this. So kind of explaining each thing. I talked about, the front end is responsible for all the HTTP requests. The scale controller is doing the monitoring, making the decisions. The data role manages the life cycle of the workers. The controllers can create, stop, and start. The FPS, or the function pod service, will actually manage those placeholder pools. And then we have state management that's done with Cosmos DB. And we have Legion, which is the actual container dispenser. So now that we have a few of those kind of primitives in our mind, let's see it come together in an end-to-end. I'm going to do two comparisons. I'm going to do a before and after. This is before, and after I'll show you after. So before we created flex consumption, these are like, if I use a consumption plan today, or if I use Elastic Premium today, or App Service today, this is what happens. So let's say that HTTP traffic is coming in. It's going to first, on the left side, it's going to hit that load balancer. It's going to hit that front end role. And then the front end role is going to basically ping the workers to see how many are there and to see if they're healthy. So it's basically trying to gauge the health of the cluster and if you have enough. And then based on that, it's going to make a scale decision using the pings. Now, what could possibly go wrong having a massive scale fleet where you're using pings as monitoring? A lot could go wrong. A lot has gone wrong. So it turns out that was not the greatest monitoring mechanism. And that's part of the reason why I think Functions has had challenges scaling and delivering the kind of instances you wanted. It's because of this kind of a mechanism. It got us, when you build a SaaS service, you kind of think about an architecture that'll carry you a year or two. But we definitely hit the point where we had to rebuild it to give you the exact experience you want. All right, so let's look at the latest approach. This is flex consumption. So flex consumption, it's a similar workflow. Traffic is going to come in through the load balancer. It's going to hit the front ends. And then new logic, instead of pinging, what it's going to do is it's going to look at what's the concurrency configuration for each of your function apps. So basically, how many events should it be able to handle per instance? And it's going to make a calculation of, well, here's how many workers you should have based on the traffic I'm seeing and on what you've told me is the right size capacity of your workers. And there's no pings. Pings are toast. So it makes a much better assessment through the control plane. And then, based on that, it can work with the data role in the back-end fleet of placeholders to create more instances. And instead of doing things in serial, it actually can do things in batching as well. So we could do batch pub/sub style processing with the requests, and we can build things a lot faster. And as a result, we can create that burst effect of knowing reliably what you need, right? You stepped on the gas. I have a lot of requests coming in based on, oh, here's how many requests per instance you want. You need way more instances. Let me create a batch for you. Boom. And then it's constantly monitoring to decide, should I give you more? Should I give you less? And it's a much more efficient system, both for you and for us. So let's talk about concurrency. I've been making a big deal about this. And I'll be honest, when I first heard concurrency, I needed my team to explain it to me. I was like, can't we use the top 1,000 most common words in the language to describe what it is. And they're like, nope, it's called concurrency. Okay. So concurrency gives us control over the number of messages per instance. So in parallel, right? So let's look at a couple examples. Let's say that I've set the concurrency to 1. What that's saying is I want each instance of a function to handle one in only one message or request. So let's take an example. If I have 10 executions coming in with a concurrency of 1, it's going to create 10 instances because it's a 1-to-1 ratio. If I cut the number of requests in half, so I send 5 instances, well, the math's really easy, or 5 requests, I'm going to get 5 instances for those 5 requests. So this is incredibly powerful if you have a high computation type workload. Like it really needs dedicated resources to compute and work on that data coming in. It's really good for that. And actually, if you look at AWS's architecture, their entire architecture is based on concurrency of 1. They're always giving you a new instance, a new micro VM for every Lambda call. And that's okay, but we're kind of proud of this one because we give you a flexible and controllable concurrency, and the whole system knows about it. So let's say now I set a concurrency of 2. That means like every instance will handle 2 events in parallel before it goes on to make a new one. So let's rerun this whole scenario. So I'm going to send 10 requests, and you can see it's doubling up. Oh, I'm going to put 2 messages in parallel in each instance, and I won't ask for more instances until I see more. If I send 5, it's going to say, oh, okay, 1 and 2 got 1. Executions 3 and 4 got another instance. Execution 5, even though it's underutilized, it's going to get a whole instance. So you can kind of see how the concurrency lets you have control over what the right size is. And we've debated, and I'll watch your feedback after, should we do automatic concurrency for you? We've totally debated it. We're worried that that's too magical and that you know more about your workload than we do, so we haven't done that yet. Our first step in this direction is we give you controllable concurrency, and what that also means, you're going to have to do a bit of testing and probably load testing, just like I did before, to see what's the right amount of messages and requests per instance. Hey, when do I hit that happy spot of CPU and memory of 70%? That's kind of what you're looking for. And I would encourage you, rather than trying to do 1,000 instances at once, see if you can crank up that concurrency and do more work in parallel. If you do, you're going to save money. You're going to be more efficient. And it'll also speed up the workload for your customers. So a little bit more information about our host. Our host not only knows about your runtime and the version and all that kind of stuff, it knows about the kind of hardware you want. And this is a change, another change in flex consumption. In consumption v1, the one that's out before, it was kind of a black box. You didn't really know what kind of memory and CPU you were using, and it was just kind of magical. But in this case now, you can actually say what instance size you want, just like you can for VMs. So we'll default you to a 2 gigabyte instance, and it has the right allocation of like 1 CPU to go with that. You can go bigger to 4 gigabytes. You can go smaller, even to half a gigabyte. And by the way, we're going to add more and more instances. We just have the 3 in beta, but we're going to add a lot bigger ones. We're actually going to see if we need to add the smaller ones. For us, it's harder to do the smaller ones. The economics for us to subdivide the virtual machines into tiny sub-machines, it's a little tricky. But we'll certainly, based on your feedback, we'll do what you want. In terms of the default concurrency, we've already run load tests, and we've looked at real workloads that are already running in functions. And this is just our observation. This is how we fine-tuned it. For that run-of-the-mill function that's a 2 gigabyte instance size, we've set that to be a concurrency of 16. We've just seen most workloads run pretty well that way. And you can kind of see it's kind of like powers of 2. So as you double the memory, we could double the concurrency. But or it's like powers of 2, basically. And if you go down to 512, we saw a concurrency of 4 work pretty well. But this is completely settable. I think this is where workloads actually will vary. Is it CPU intensive? Is it I/O intensive? You have to kind of decide, and you can set that concurrency. But at least it's like one knob. It's not a whole bunch of knobs anymore. Python has a concurrency of 1 by default. We did this because Python has, I won't use the word unfortunate, it has its own point of view about threading and how many threads can run per CPU. So in a serverless environment, that's pretty tricky. And just to keep you out of trouble, we've set you to a concurrency of 1. And that way you won't run into any of those tricky issues waiting for the CPU. So Python's a little bit different. But if you take some small instances with a huge scale out, you can still run Python workloads quite well. And we have some super huge AI customers that are already doing that right now. So far, so good? Makes sense? All right. So let's look at the concurrency control. We'll pop out a PowerPoint. I have a different kind of a demo for this one. So here in VS Code, I have a demo that's basically data ingestion, but the data ingestion is going to it's going to take prompts from the user, and the prompts will have actual files, like files that you want to analyze with AI, and it will ingest those big chunks of data, and then it'll do the processing on it, and it'll do RAG. To give you kind of a user example. So we have a front end, and the front end will take the files from the user. And if you've seen our AI demos, this is going to look similar to probably every AI demo you've seen. So in the RAG scenario, I'm going to take my own files. I have all this health data. Let's take 10. And I'm going to upload a batch of them. Oh, did I take down my function? Or am I looking the wrong one? One sec. I did a deployment a second ago. I'm definitely keeping it real because stuff fails in reality. One second. So I just created this one, and I should have a static web app. That's the front end. Is that the one I was? Woody Meadow? Woody Meadow. All right, let's take a quick look. We won't spend too much time debugging this. My functions are healthy. That does not make sense. Let's just try it again. It's the cloud. Sometimes you just have to try things a couple times. So take a file. We'll ingest it. No. Let's see if we can ask a question. Does my plan cover eye exams? Okay, complete. Paul is like crashing and burning. That's okay, hopefully. I've got a different kind of a demo. Forget you ever saw this. I apologize. I don't know why it's not working for you right now. But I have yet another example of concurrency that I could show you because I was anticipating something could go wrong. All right. Did I turn on hard refresh of the website itself? That's a good idea. Let's do a full refresh. It's making me auth again. Sir, I salute you. Thank you. You've used Azure, so you know you have to try and refresh again. Thank you. I'm in a very forgiving mood, so we'll take that one. OK, so let's actually try ingesting our data one more time. OK, so things seem to be working end to end. Now let's do that trick. So we're in AI Oslo, and let's watch our function through the lens of monitoring. So we're going to go into live metrics. On this tiny screen, it's going to be interesting. Let's see if I can pull this off. So we'll do this, and then I can do like tile to the right, and I can do like tile to the left. All right, so let's see if we can force some spikes with the concurrency. So let's upload one file and watch it. I think in this resolution it's going to look not so awesome. There we go. So you saw one request went in, and this is it's a little bit of a bug, but right now if App Insights is monitoring your functions, there's like an inspection effect, and it's causing instances to scale out. So it's a bug. We got to work on that. But that's actually what's going on. Just notice that it's kind of a small number of servers. OK, so it cooled down. We're back at 3. It should be at 0, but I'm inspecting it with monitoring. It's not 0 right now. Sorry about that. All right, so let's do it again. And let's add 10 files. All right, watch here, watch here. Here we go. OK. That was a little counterintuitive, but I was expecting to see kind of a 1-for-1 ratio, because what I've done is I've set I thought I set the concurrency to 1. Let's actually double check that. Remember, a concurrency of 1 means every one event gets its own server, it gets its own instance. So if I look at my function, you probably know this. If you go to the JSON view, you can see the actual like ARM control plane view of the resource. And I can see, oh, how the heck did that happen? A concurrency of 16. Am I in the wrong resource group? That's a good question. I am in the wrong resource group. I think I'm trying to do too much at once. Let's see. Let's go back here. I appreciate you bailing me out, though. So we'll look at the function. All right. Now, HTTP scale is going to be set here. So this has a HTTP per instance concurrency of 5. So we have it lower. It's not all the way down to 1-to-1, but that was lower. That's why we saw some instances, but not a huge amount. And then this is an important thing you need to know about how functions work. HTTP scaling is done different than message scaling. And it kind of makes sense if you think about it, because HTTP gets monitored by our front end in our load balancer. That's how we know how much traffic is coming in. There's really no other way to know. Messages are different, because we need a way to interact with the actual backend, like the message broker, the queue, et cetera, that you're working with. And what actually does that in functions is the Azure SDKs. Like if I'm working with a service bus, it's the Azure SDK for service bus that functions internally is using to keep a connection alive to that message queue. If it's event hubs, which is the case here, I'm using the Azure SDK for event hubs. And you probably also know this, but Azure triggers and bindings and functions are actually just wrappers over the same SDKs that you all have. They simplify and they give you context. And if you use our triggers and bindings, it knows things like concurrency. It knows things like the state of the function, which give you some extra advantages for scaling. But what that kind of means is we need to configure in a different way if we're going to work with messages. And so the way we do that, this came out with target-based scaling, if you followed that a year ago. But we have sections in the host.json. So this is a configuration that goes with your app at deployment time. Right now, that configuration lives here. And event hubs, you might know this too. Event hub is actually a specialized kind of service bus. So the configuration for event hubs and service bus is the same. It'll be in this block called service bus. And that's where I can set the max concurrent calls to 1. So just things to be aware of. You've got to think about concurrency for HTTP and think about it separately from your messages. And so that's how I set it here. Now, maybe we can do one more cool example. I'm going to let this one kind of brew because it takes 2 minutes and I'm going to run out of time. All right, so I'm going to switch gears. I made 2 more end-to-end demos. So remember the first demo I did where we had the event hubs and it was like 2,000 requests per second? So that has, by default, a concurrency of 16 if you take the defaults. So I have 2 experiments here. I have one with a concurrency of 8. So less messages per instance means more instances. So let's run the load test for this guy. So go to my load test. And I'm going to rerun it. You can see I actually ran it right before this demo, right before this session. All right. And I'm going to rinse and repeat. And I'm going to do that for the concurrency of 32. Here it is. We're going to go into the function. We're going to go into the load test. All right. And these have a little bit of time that they need. So let's do... Let's go here. Let's go into the live metrics. This is the live metrics for 8. And we don't see it running yet. Still provisioning. And I'm going to do another side-by-side. Can you imagine the amount of infrastructure you used to have to do this kind of thing? All right, so let's do... Was this the 8? Yeah, that was the 8. So let's do the 32. I'm racing against the clock. But what I'm wanting to see from this experiment is, can I keep the request rate as high as I want? And if I force the concurrency down, I'm going to expect to see more instances, and I'm going to expect to see less strain and stress on my hardware. Whereas in this case, the 32 case, I'm going to try packing more concurrency or more events in, and I want to see if I can still right-size it without blowing up the machines. And this is going to let me do that kind of real-time cost analysis. I'll tell you what, let's flash away for a second, because I literally am going to run out of time. So we'll flash forward. I think I wanted to tell you a little bit about placeholder pools. So the way that we pull that off... Oh, shoot. Let's just keep it not zoomed in mode. So again, to keep this really fast, we keep pools or fleets of servers. And for every application you have, for every runtime you use, we actually manage different fleets. And that way we can have a ready warm pool available for that kind of permutation of compute that you need. And then we have a process called specialization. I'll leave you with the slides. But specialization is the process of slamming your application zip file on top of an already warm VM and container. And that's how we effectively give you the faster cold start times, more in the hundreds of milliseconds versus in minutes. There's a lot of trickery we have to do. Like I'm kind of trying to represent by the colors. We need to keep track of all your apps and versions. And if your app cold start time gets slow, one of the reasons could be that you're deploying an app that didn't expect. Let's say you configured a .NET 8 app and you deployed a Python app. It's like, oh, I can't find the placeholder pool for that one, and it's going to be slow. So that's one of the tips and tricks I'm going to leave with you. Okay, let's come back here. So here's our A/B test. Again, to remember, this is concurrency of 8. We're doing 40,000 requests per second, not too shabby. Look at the servers. We're up in the hundreds. And let's look at the CPU and memory. I'm not so happy about that. Look at that. I'm like 10 to 20% utilization. That's not good, right? We can do better than that. So now let's look at our A/B test over here. I've got a concurrency of 32. I have to think about why the request rate is different, but it should be the same. Depending on the point in time, it should ramp to the same number of users. But look, I'm using far less instances, and I'm getting closer to that 50% utilization. So what this actually tells me, for this particular workload, which is just light ETL, light telemetry ingestion, I'm going to want a higher concurrency, which will make my bursting faster, because I have less to burst to, and it's going to make my costs lower, because it's just less compute time in parallel that I'm running. So I think this is hopefully a good visualization of what you want to do. And with that said, I'm going to, I guess I'm over by 1 minute, apologize. So I'm going to leave you with some tips on how to scale. Like if you want to achieve maximum scale, you do want that 1-to-1 ratio of function apps and functions within in a function plan. That means that every single function can have horizontal scale. Think about it this way. If you have multiple functions in a function app, it's sharing. It can have noisy neighbors. So that's another element besides the concurrency. You're better off to choose small instance sizes and scale out versus big instance sizes and scale up. That's going to save you money. Chances are you're overutilizing your VMs. That's not always true, but that's a lot of the times. Watch out for your logging. I didn't get to go into it today. Your logging can actually be a reason why your scaling will fail. So make sure that your steady state logging is the minimal logging you need, and rely on trace level of information, verbose, or debug for the cases that you really need to troubleshoot something. And the rest of the time, keep it at a normal tracing level. And I have a cheeky joke, like you could order some coffee because you won't have time to pay attention to that. For cold start, some other tricks. I'll leave you with a whole article on it. But flex consumption does this best practice, but you can do it for all functions. Make sure you deploy with the run from package equals 1 or run from package equals URL. The biggest determiner of cold start time, since we make those placeholder pools, is actually how fast we could load your application zip. So by using this mechanism, you're simply loading a blob. And as long as your blob is small, your app is going to load faster. So I think this one can really, really help you with cold start. And that said, everything we went through here, the source code, the notes, the CLI commands, and more, is on this gist. And I'll make it better and better based on your feedback. With that said, thank you so much for spending an hour talking about scale. See ya.